không thể phát hiện được. Sẽ cái gì sẽ
Okay, Ray, can you see the YouTube video? Yep.
Yes.
Okay, we watch a short video, then we will start the new topic.
Illustrations to show atomic spectra. I'm going to show the spectrum of an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements: mercury, nitrogen, neon, and especially hydrogen. Hydrogen will be important in the labs and in many other applications. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating just like a street grate. It has lines through it. And this allows you to resolve the spectrum of a source of light in the same way that a prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with the diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present in this. You'll see, as you look on the right side, violet through all the colors of the spectrum all the way through red. So that's a continuous spectrum. We'll try next to look at a discrete spectrum of mercury. Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So I'm going to locate this, its proper spot, turn off the continuous spectrum. So this is a mercury spectrum without the diffraction grating. And let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum. Next we will try a nitrogen spectrum. I'm using this fur to prevent burning flesh. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. That's nitrogen. Two more. This is neon. There's a beautiful orange look to it, and when the diffraction grating is in place, you see a large number of red and orange lines. This is exactly what's used for neon lights. The original neon light was made out of neon like this. There are other gases that are used to form signs, but neon was really where it started off. It has a beautiful, bright, reddish-orange spectrum. So this is hydrogen. It has a reddish cast to it. And when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line. And it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines. Then there's a turquoise colored line, greenish blue is the hydrogen beta line, both from the Balmer series, and we'll talk about those, or have talked about those in class. And then finally, the hydrogen gamma line is a
Okay, are you with me, Ray?
Yeah.
Be unstable. Just now we look at the discharge tube with different vapor, mercury, nitrogen, neon inside them, and then we see the different spectrum there. Right? Hydrogen also, hydrogen spectrum. So let's start our lesson. Energy level in atoms and line spectra. Existence of discrete energy level in isolated atom. Distinguish between emission and absorption spectrum. And then use this formula. Hydrogen spectra lines, HF equals to E1 minus E2. Page 233. Right, that's the syllabus. How do you explain the emission line spectrum? Right, this is continuous spectrum. This is the spectrum of sodium, hydrogen, calcium, mercury. It's unique. They are different from each other. So we can use this spectrum to identify the element. Okay, let's look at hydrogen. There's a continuous spectrum from 400 to 700 nanometer. Right? Hydrogen. These are the different wavelength for hydrogen spectrum. This is the emission spectrum of hydrogen. This one. This is the absorption spectrum. It's the same, except the background is dark. Whereas this absorption spectrum, the background is same as this one, except these are lines correspond to each other. Dark lines correspond to the color line. These are lines, these are wavelengths that have been absorbed by hydrogen gas. Right? We go over that in a while. Okay, here we have a bulk, high density hot metal passing to diffraction grating. We got continuous spectrum. Right? We have a hot gas passing to diffraction grating. We see emission spectrum. And we combine these two together. That means continuous spectrum pass through cold gas, pass through diffraction grating, we get absorption spectrum. Okay, there's the emission line spectrum, continuous spectrum, there's the absorption line spectrum. Spectrum, singular, plural is spectra. What is it? Any particular distribution of electromagnetic radiation, such as the display of color produced when white light is dispersed by a prism or diffraction grating. Example, continuous spectrum of white light has all the colors or wavelength of white light between two limits. 4 and 10 to the power minus 7 violet to red, 7 and 10 to the power minus 7 meter. Okay, so that is your, if you use prism, it is the color that you see. continuous spectrum. A hot, opaque body, such as a hot, dense gas or solid, produce a continuous spectrum, a complete rainbow of colors. Dense gas or solid, right? It must be hot to produce continuous spectrum. It's just to review your AS work. Our instrument is not so sophisticated as what we see in the YouTube just now. Right? There's your whatever source you want to analyze, you pass it through, then there's a zero. So zero will be all the color together combined. Then we usually will look at the order N1 N2 N1 either side right? N2 usually very difficult to see be too far apart. Okay, so that's your first central white and first order, second order Let's see if we use continuous laser light or continuous spectrum then that's what you will see. Line spectrum. Right? This is called emission line spectrum. Consists of thin vertical lines of different color. Thin vertical line of different color set against a dark background. That's dark background. Each line corresponds to a value of wavelength emitted by the source. So each line or each color represents a particular wavelength emitted by the source. Then if we observe, right, this violet, that's red, longer wavelength, shorter wavelength. So this part is closer together. And distance between the lines get wider and wider at higher wavelength. At higher wavelength, they are far apart. Right? These are close together. It becomes wider and wider apart. Longer wavelength, wider apart. Obtained from hot gas. Okay. Hot gas pass to diffraction grating, we see the spectrum, line spectrum. Absorption line spectrum, same, it's the same, except you see dark line. Consists of dark vertical lines set against a background of continuous spectrum. What does it mean? Dark lines are wavelength of electromagnetic radiation absorbed by the gas. That's a continuous, this is the emission from the lamp, continuous spectrum passing through cold gas, diffraction grating, and that's what we see. Emission line spectrum of hydrogen, right, ELS. Each pattern of line is characteristic of the element in which produce the light. You can see helium and hydrogen completely different spectrum. This hydrogen, this one is helium. Pattern of line emission spectrum can be used to identify the type of atom produce a spectrum. So we look at the line spectrum, then we can identify whether it's which element is being observed. Right? These are given by gaseous atom or isolated atom. Dark lines in absorption spectrum correspond to the colored lines in the emission spectrum of the same gas. Right? You can look at this is the absorption spectrum, this is the emission spectrum, they correspond. Okay? Because these are dark lines represent wavelength that is absorbed as you pass through the cold gas, whereas this one is emitted by the hot gas, hydrogen. What can we deduce from the observation? Each line of the emission line spectrum corresponds to a value of wavelength. Each line represents a particular wavelength of electromagnetic radiation emitted by the gas. From Planck's law, the energy of photon of frequency f is given by E equals to hf. Right? These are the color lines. We can determine either using wavelength or frequency the energy. Right? So each line represents energy. For an atom to emit radiation, there's energy. The atom must move from a state of high energy to one of low energy. Okay? If it's going to emit energy, it must have energy first in the first place, excess energy. Okay? Move from a higher energy level to a lower energy level. Right? There's higher energy, there's lower energy. So the electron, if it's going to emit energy, must move from a higher energy to lower energy. And then it emits electromagnetic radiation, a photon of electromagnetic radiation. Since the spectral lines are discrete, right? Spectral lines are discrete, we can expect the energy level to be discrete, right? The lines are discrete, so energy level must also be discrete. Electron transition, the excitation, right? Higher energy level, En plus 1, En when an electron moves from a higher energy level, En plus 1, to a lower energy level, En, the electromagnetic radiation of frequency is given out. Okay? So it moves from higher energy to lower energy, that's the energy that's given out. And that energy is equal to the photon of electromagnetic radiation. Supposed to remember and recall this equation. Okay. Right? The excitation go from higher energy to lower energy. So electromagnetic radiation is emitted. So the energy different, that's the energy different equals to electromagnetic radiation, energy of electromagnetic radiation. Your syllabus use different symbol lah. E1 is lower one, E2 is a higher one. So usually if you use E1 minus E2, you don't bother about the negative sign there. Okay, same thing lah. I use a higher one minus lower one to eliminate the negative sign lah. Okay, these are all in negative numbers. All the colored lines are electron moving from higher energy level to lower energy level. The lower energy level is all the same. This is the lowest energy level. This is a different color line. Right? Red one. This is the red one. This is the green one. Right? More energy, higher frequency, shorter wavelength. And this is energy level. Energy of the energy level. When an electron moves from a higher energy level to a lower energy level, a photon is a particle of light, is emitted. Light emitted this way from movement of charged particles is called radiation. In this case, it's the electron moving from higher energy to lower energy. So it emits a radiation. Right? Higher energy to lower energy. So we show electromagnetic radiation emitted. A photon of light is depicted as a squiggly line. Squiggly line with an arrow at one end. That's a picture show. This is what the author calls squiggly line. Okay. Right, these are our energy level. They are discrete. Energy of electron is said to be quantized. that is electron are allowed only in fixed energy level. They cannot have any energy, but they have only, right? They could be quantized, or electron are allowed only in fixed energy level or shell or subshell. Emission and absorption line spectrum are evidence of existence of electron occupy energy level in atoms. Okay, electron transition. This one is excitation. That means right? It has to gain energy for it to move from a lower energy level to higher energy level. And that energy is from the electromagnetic radiation. In excitation, an electron moves from a lower energy level to a higher energy level when the electron receives energy from the external source. This is from the external source, electromagnetic radiation. Ionization energy is the greatest energy. Different for hydrogen is about 13.6 electron volt. Right? This is usually we call it E naught lah, the ground state lah. And then this one will be E infinity lah. Right? E infinity is zero energy lah. So from the ground state to the highest energy level for hydrogen is 13.6 is the ionization energy. This in the ultraviolet region lah. Any comment or any question?
No.
Okay, calculate what is the frequency and wavelength of light emitted when an electron falls from energy level 7.92 times 10 to the power minus 19 to energy level 4.23 times 10 to the power 19. You can get the answer. Right? Using the formula that I've given you. Right? Just draw a picture or picture in your mind what is happening. This higher energy level, this lower energy level. Usually it's a negative sign. We will go into that in a while. This is formula. High energy level minus low energy level equals to the frequency of electromagnetic radiation. Higher minus lower, 10 to the power minus 19. Planck's constant frequency. For this topic, you need to remember this formula. You can calculate lambda. Can.
Yes.
Clear. Energy levels of hydrogen, page 232. Yeah, just like rungs of the ladder. Right? When we think of energy level as rungs of a ladder, these are analogy lah. For a person to climb each rung, he needs a specific amount of potential energy. Go from one to the other, you need a specific amount of potential energy. He cannot step between the rung, right? In between, he cannot step there. Energy of electron. Electron in atoms can occupy many different energy level. The further away an energy level is from the nucleus, the higher its energy. So an electron occupying energy level E4, E4, that's a E4. In this picture, would have a higher energy than electron occupying any of the other three levels. Right? So this is higher energy, this is the lowest energy. So this is the highest one, E4. Energy levels for hydrogen Energy levels are certain energies which electrons are permitted by wave mechanics to process. Don't worry about wave mechanics lah. This one is a mathematical analysis which you study in university. Energy levels are conveniently expressed in electron volt. Right? So 1 electron volt is 1.6 and 10 to the power minus 19 joule. The energy levels of atoms are usually represent a series of horizontal lines. The spectrum of hydrogen is particularly important in astronomy because most of the universe is made of hydrogen. Emission or absorption processes in hydrogen give rise to series which are sequence of lines corresponding to atomic transition, each ending or beginning with the same state in hydrogen. Thus, for example, don't worry about the name. Balmer series involve transition for absorption or ending for emission. For the first excited state of hydrogen, while the Lyman series involve transition that starts or end from the ground state. We'll go into that, explain that in a while. Okay, these are the spectrum of hydrogen. The energy level, right? You look at Balmer series, right? All of them will go to the bottom there, right? The lowest energy level. So that's our E2, energy level E2. And then N is just 1, 2, 3. Since the emission line spectrum is discrete, we can expect levels to be discrete. Right? Show you how they are related. Okay. The spectrum, you just invert it. Shorter wavelength, longer wavelength. Longer wavelength is the bottom there. Shorter wavelength is at the top there. They are closer together. Energy level are also closer together. That is your energy level for hydrogen. Don't particularly worry about the name of the series. Right? Just know how to calculate. Right? These are all energy level. Right? The lowest one is a ground state. Ground state E1 is minus 13.6. Right? Between the energy level is a forbidden gap. The electron cannot have energy within this region. It can have energy in the energy level there. Minus 3.4. Oh, another one there. Right? We come from the bottom. N equals to 1, E1. N equals to 2, E2. Okay, so between the first level, the ground state, and the first energy level is 10.2, which is ultraviolet in the ultraviolet region. These are any level, energy level higher than E1 is considered as excited states. So all these transition, you need visible light. All these transition called Lyman series, you need ultraviolet light for it to go from ground state to the first level. Right? And this energy, the lowest one is 1.8 electron volt. This is in the visible region. Energy levels are certain energies which electrons are permitted to have. Right? Electron can have any, so certain energy levels, that's all. They are horizontal line. Represent the horizontal line. Balmer series is in the visible spectrum. Lyman series is the ultraviolet. Right? Balmer series visible. This one Lyman series ultraviolet. All levels have negative value. Negative value. The lowest state is called the ground state. or stable state lah, lowest energy. Right? All these are excited state lah, all greater than E1. This is a forbidden gap. These levels are characteristic of particular atom. Right? This is for hydrogen only. Okay. Minimum excitation energy is 10.2 to go from a ground state to the first energy state. Because of the details of hydrogen's atomic structure, Gamma series is in the visible spectrum, Lyman series ultraviolet. The diagram illustrates some of the transition. This is called excitation in the Gamma series and Lyman series. All levels are negative value because external energy has to be supplied to remove an electron from an atom. The electron is trapped within the atom by attractive force of the atomic nucleus. Right? So the nucleus is positive, electron is attracted by the positive nucleus. So you need to provide energy for the electron to escape. Stable or ground state of atom is the condition in which the energy is in the lowest. This is the lowest, cannot go any lower. Right? For hydrogen is minus 13.6 electron volt. Excited state is any state lah, greater than 2. An atom cannot have any energy level cannot have any energies between the levels called the forbidden gap. Right? Electron cannot be inside this region or inside this region, only on the energy level. We are just repeating. Ionization energy is the minimum energy required to ionize an atom, which is in its ground state. The electron is just become a free electron. Right? So for hydrogen is 13.6 ionization energy for the electron to be free electron. Okay, remember to pass out your assignment 3.
Okay. I actually done most of it already.
Okay, good. Excitation energy required to raise hydrogen atom from the ground state to another energy level. Minimum is 10.2. This means that the minimum energy for excitation is electromagnetic direction from ultraviolet spectrum. Thus, we will not obtain emission spectrum for hydrogen if it is transparent to white light. Right? If we shine white light through hydrogen gas, it will not cause any excitation because the energy for visible light is about 1.8, very much less than that. Excitation energy is the potential required to raise the electron to the excited state. Right? So it's 10.2. Right? We will cut off at any time now. So this one just summarize for you. Okay, you can read yourself.